All right. Welcome, everybody, to this week's GOCC. We're very happy to have CERN, who's going to be telling us about RSK and growth diagrams.
Yeah,
Before we begin, I want to, sorry, before we begin, I want to reiterate our community statement. We're all learning, everyone has something to contribute, and no one has all the answers. So with that being said, CERN, take it away.
yeah, thank you for inviting me. I'm contributing a chicken and an egg today. I'm gonna talk about RSK and growth diagram, and like for me, they are very interchangeable. And the examples I give today will be based on my two works, one joined with Daki Huang and one currently in progress with Challenge U. Um, so let me just quickly review the RSK correspondence. In this case, just RS. So you take, can you all see my mouse actually? If I point here, will people see it? Okay. Yeah, if I take
Yes.
a permutation in Sn, the correspondent will send it to a pair of standard Young tableaus and they have the same shape. And the way I do that is to get the first one, I just do insertion. So I go, just for example, here my permutation is 3, 4, 2, 1, 6, 5. And I just go like one by one. So here I start with a 3. I just insert it in because there's nothing there. And I go to the next one and I will try to put it to the first row. And here putting the 4 in the first row makes sense. So I can just put a 4 there. Then I go to the 2. Now, if I put the 2 in the first row, it wouldn't make sense anymore because 2 is smaller than 4. So I find the first thing in the first row that is greater than 2, and I put a 2 there. And because I do that, I have to like bump the 3 down. So the 3 goes to the second row, and so on. So next I put the 1 in. 1 we have to kick the 2 out. The 2 gonna have to kick the 3 down, and I get this thing. And then I just put 6 and 5. And the final thing I have here is my what we call the insertion tableau. We usually call it P. And to get the second tableau, all I need to do is I like keep track of the new box I have every time. So here, this is my first box, so I put 1. This is my second box, so I put 2. This one I put 3. This is the 4 and 5 and 6. And my second one is called the recording tableau because it's recording the new box I add each time. And let me see if I can clear this. Okay. So what I want to do is um, there's a growth diagram for this. And the way we do the growth diagram is you take your permutation, you draw a square like this. I usually put like the empty in the left and in the bottom, and you put the axis in according to your permutation. So this is 3, this is 4, this is 2, this is 1, and 6 and 5. And then I fill up the rest of the diagram using my setup local rule, and I get something like this. And let me do some example. So for example, here I have an X. So the rule say I just to go from this to this, or I mean, I can even go here, they are all the same. I just add one box to the first row. So this is 2, 1, 1, add one box to the first row, get 3, 1, 1. Let me find another example. This one, there is no X, so I have to use one of the cases here. These three are all different. So I'm in this case. And so to get this one, I just take the union of these two. So I get this shape. And let's see, this is the hardest one, I guess. So this one, these two are the same, but they are different from lambda. So I'm in this case. Then I compare these two, and this from here to here, I add a box in row 1. So from here to here, the rules say I have to add a box in row 2. So I get this shape. Okay, anyone has any question about my growth diagram? Okay, okay, cool. And what I get at the end is if you follow this um, right column and you keep track of the new box you have every time, then you get this tableau. And if you recall from the first slide, this is my insertion tableau. And similarly, you can do the same. You go along the the top row, then you get the recording tableau. Okay. So Yeah, so when I gave this talk at MIT, a grad student asked me, like, why is it simpler than just doing insertion? Like, why do we have to draw this big thing and like have some maybe complicated local rules? And one answer for that is that in this thing, you have a 2D thing. You have no like time dimension. You don't have to keep track like, okay, put this one here. I have to follow the insertion path. Like when you want to prove something, like you don't have the time dimension. You just have a very solid 2D grid. And so you can get a lot of properties like easily in this way. So for the classic one is if your permutation W correspond to PQ, then you invert it, it will correspond to QP. And the reason is just you when you invert it, you just like flip the growth diagram. So obviously, by symmetry, we get like P and Q and Q and P. And yeah, this idea of like doing growth diagrams, you can apply it to like almost any like algorithms on these tableau that you can do. So for example, if you want to do JDT, you can draw some sort of diagram like this, where this is like the order you do JDT, this is your skill tableau, and then you fill up this direction, then you get the result JDT will be here. Or if you want to do evacuation, you put your tableau here, and this size like what you get after evacuation. So you have a lot of like beautiful proofs. So for example, evacuation is an involution, and from this growth diagram is very clear. Like you do it one way, you get to the other side. You do it again, you get back to the original side. Um, so that is the first reason. And the second reason I usually call it like growth diagram remembers the geometry. So if I have, let's say I have two flags with some relative position indexed by this permutation. And I take a generic nilpotent operators on both of them. So this means that I have a flag E1, E2, E3, and so on. My sigma here will send like E2 inside E1 and so on. And then each thing on the growth diagram will tell me the Jordan form of my operator restricted on some subspaces. So for example, if I'm looking here, this is telling me what the Jordan form of that operator on E3. This one is like F4, and if you take something in the middle, it's like E3 intersect F4. So all of the information about geometry is like captured inside this growth diagram. Um, yeah, any questions so far? Cool. So yeah, this is where I get to the chicken and the egg. So if you have a chicken, aka some RSK algorithm, you can always draw the growth diagram. So all you need to do, like, I know my recording tableau. So all I need to do is put on the top row my recording tableau. And if I want to know the the thing in this position, I can use geometry to tell me what Jordan form I want, or I can just like insert this subword and it will tell me the shape I need to put in this corner. So if you know RSK, essentially you know the growth diagram, you know everything, and all you need to do is guess the local rule. Then you would get the growth diagram. And similarly, if you know the egg, so if you know something in geometry, the egg will tell you again like what you need to put in each corner, and then you can use it to, some people just use it to define RSK. Like they say RSK is this growth diagram, but also sometimes the growth diagram will be very nice and you can like come up with the RSK algorithm just from the growth diagram. So yeah, you know one thing, you know the other. For me, they are the same. But yeah, the question is like which one came first, chicken or the egg? And so today I'm gonna give like two examples. One where I know the chicken and get the egg, and one I go the other way around. Um, yeah, so the first example has to do with Schubert polynomials. It's called Schubert RSK. And there are many ways to define like Schubert polynomials. My favorite way is to use Publius pipe rim. So this thing is a Publius pipe rim. I have some pipes. come in from the bottom here and then go up to the right. My pipes can go like however it wants. I can use any square I want. The only thing I am not allowed is have a square like this. So that's why it's called pumpless. And I also only consider reduced pumpless pipe rim, meaning that I don't allow any two pipes to cross more than once. So like these two cross here, then in the future they cannot cross anymore. And if I get a pumpless pipe rim, I can take the weight of a pumpless pipe rim by just counting how many like empty square I have in each row. So here, from row 1 to row 4, I have one empty square each. So my weight is like x1, x2, x3, x4. And to get Schubert polynomial, all I have to do is to sum over every pumpless pipe rim that gives me the same permutation and take the weight of them. So if I want Schubert of 2, 1, 4, 3, these are the only four reduced pumpless pipe rim I can do. And their weight is like, holy, did I draw something wrong? Okay, this one should go here for some reason. I think I drew something wrong here. Oh, these two are the same. Okay, silly me. So this one should be here. This one should be here. And then there is another pumpless pipe rim that's supposed to have. Okay, so this one should be like here. Sorry for this. But yeah, you get the idea. And if you don't, this is a good time to ask a question. Okay. So there's a rule that is very common in Schubert called Monck's rule, and it's saying that if I take the Schubert polynomial of one simple transposition and I multiply with like some Schubert polynomials, I know what sum of Schubert I get, and the sum is given by this. So here in this example, I want S3 multiply like 3, 4, 1, 2, 5. So what I do is 2, 4, 1, 2, 5. I sort of like put a boundary between the 3 and the 4, so at the third gap, and I look how many ways I can swap numbers across this boundary so that I go up exactly one level in the strong Bruhat order. In this way, in this case, I can swap 1 and 2, or I can swap 4 and 5. I think that's it. Hopefully, I'm not wrong again. But what I would get is this product will be the sum of these two Schubert. Okay. And what it means is I can, if I want any Schubert polynomials, I can sort of like take like some some product of some simple transposition. So for example, if I want this Schubert polynomials, I can take product of these and I get a copy of that Schubert and maybe something more. And each of these Schubert of simple transposition is just a sum of x1 to si. So what this is telling me is I have this product and some of the monomials will contribute to the Schubert polynomial that I want. So for example, here I take x2 from this one, I take x2 here, I take x3 here, I take x2 here, and I get these monomials. And maybe this monomial will be in here, maybe not. But some monomial will contribute to my Schubert polynomial. So the question is, how do we know which monomial contributes to this Schubert? And the way we do that, the technology to determine that is called Schubert RSK. So to do Schubert RSK, the input would be a byword. So a byword is something that looks like this. You have like two rows of numbers, very similar to RSK. And the top row is smaller than or equal to the second row. And the output of my RSK would be one insertion from this pipe ring. This would tell me which Schubert polynomial it contributes to, and a recording chain of the permutations I get along the way. So for example, and the way I insert is called right insertion, and it's a long algorithm, and it's best to explain it in an example. So for example, if I have this published by Brim and I want to insert this byword 13, what I do is I start in row 1 given by my B here. I would start at the leftmost curve in this row and I droop. So I droop this pipe down. And then because I droop down, like there would be a bump here and I don't allow that. So what do I check? The first thing I check is I check if this second pipe exit in row less than or equal to K or not. In this case, this is true. So what do? I sort of like move this dot from this pipe to this pipe, and I keep grouping. I group down here, and here I also have a bump, but these two have crossed before, so I swap this bump and the cross, and I keep grouping. And now at this point, I also have a bump, and I check this again, and now this pipe here exit in row 6, which is greater than 3. And when I see that, I am finished. So I just change the bump into a cross. And this is the result in harmless piping. Okay, any question about this algorithm? Okay, so if I start with a byword, all I need to do for RSK is just doing all these try insertions. So I insert 2, 3, I get this pumpless pipe rim. I insert 1, 2, I get this pumpless pipe rim. I insert 2, 2, I get this pumpless pipe rim. And this thing, I would call it my insertion pumpless pipe rim. And to get the recording chain, I just record the permutation I get along the way. And the theorem say that if you fix a recording chain and you take every byword that give you the correct published pipe rim of the correct permutation, and then to sum the weight of this byword, meaning like product of the first row, you get the Schubert polynomial. This is exactly what we said before of choosing the correct monomial contributing to the Schubert polynomial. So for example, in this one, I fix this recording chain. These are all the bywords I can do to get this recording chain. And I take the product of them, the sum of their weight, I get the Schubert polynomial I want. But any question about this? Yeah, so this is my RSK. And when I have my RSK, I can draw the growth diagram. I don't know what the local rules are yet, but I know the growth diagram have to look like this. So I'm gonna put identity along this left column and the top row. And according to my byword, I would put the axis. So 1, 3, 1, 2, 2. And for some reason that I'm not discussing today, I would also put along this column the second row. So like 3, 3, 2, 2, 1. And I know this is my growth diagram. So all I need to do now is to find the x, meaning I need to find my local roots. And also, another thing I would have to explain to you is I told you that the insertion, the result, would be a published pipe rim. But here on this side, what I get is a change of permutation. So you would ask, how the hell is this chain of permutation a published pipe rim? So I would have to also explain that, and I will explain that first because that would also help explaining the local rules. So how do we get this right chain? And to answer that, we would have to come back to normal RSK. And let's say you RSK some word into a standard Young tableau, and you remove the smallest letter, so you remove all the ones. What tableau would you get? Anyone has any suggestion? So if I input like 1, 3, 1, 2, 1, I get some standard Young tableau, and I remove all the 1, I only insert 3 and 2, I will get another semi-standard Young tableau, and they are related. And the answer is doing Cheratakang. So we can also do Cheratakang on pumice pipe rim, and this will actually be a generalization because that would restrict to the normal Cheratakang for the Grassmannian case. So how do we do Cheratakang? You start at the first row that has an empty square, and you start at the rightmost empty square of that row, which in this case is this square, and you look at the pipe next to it. So I would look at this pipe, and there are two cases, like either it has to go straight down or it has to turn somewhere. So if it doesn't go straight down, meaning it's turned somewhere, then I group it up like this. And now I'm looking at this one again. And now this, in this case, it goes straight down. So there is some other pipe going up from that column, and they would need to cross somewhere because this one goes straight down. And so I know that what I'm gonna do is I'm gonna replace this by this. So in this case, I would get this. Okay, any question? And also because I swap like this,
I think
my
there was
new,
in the chat
yes,
a little earlier.
wait, we have a chat, something in the chat. I can't see the chat, sorry. Is it easy to see why the map is reversible? But Tom, can you tell me what the map is?
Oh, sorry, that was going back a few slides. I don't want to interrupt your flow. That was going back to when you first showed the algorithm for Schubert RSK.
Oh, okay. Is it this one?
Yeah.
Yeah. Uh, yes, I think so. Because when you have right insertion, you also have like inverse right insertion, which is like going backward.
Hmm.
So I think it should be easy. And also because at the end you replace a bump by a cross. If you fix a recording tableau, then when you want to go back, you know exactly which cross you start at. You just uncross it and then going backward in the insertion.
Hmm. I
Uh,
see.
yeah, thanks for the question.
Not at
Uh,
all.
yeah. Okay, where was I? Okay, any other question about my HDT? Yeah, something I want to point out is because the way I swap it, the new permutation will always be related to the old permutation by a simple transposition because I am sort of uncrossing these two pipes that are next to each other. And so if you start with this pipe and you do ChatGPT to get rid of every empty square in the first row, you get this one. And the permutation of this one is this, and you take out all the empty square in the first row, you get this pumice pipe rim, and the permutation would be this one. So if you want to go from here up one row, you just do JDT to get rid of every empty square in the topmost. And if you want to continue going up, you just keep doing JDT on the second row and so on. Okay. Yeah. And also because of the same thing we said before, if I do JDT to go up, these two permutations will be related by a sequence of simple transposition in increasing order or decreasing order, whatever, depending on which way you look at it. So now I can tell you my local rules, and there
A
will be some rules.
question
Yes,
before
go
you
ahead.
continue. The only permutation for which the bumpless pipe rim does not have any empty squares is the identity. Is that true?
Yes, that is true.
Okay.
Yeah. Oh, any other question? All right. So yeah, I can tell you some rules. And again, I know these three permutation, and I want to find the fourth one. And some rules are very simple. So for example, if these two are the same, then these two are just the same because there's nothing to do. And similarly, if these two are the same, then these two should be the same. The third one is more complicated. So let me do the fourth one before I go back to the third one. So the fourth one is when you have an X here. then what you know is these two are definitely the same. You know that these two are related by some simple transposition. So to get from here to here, I would have to do S4 and then S2. So I would let I to be the set of the simple transposition that I do. So my I here will be 2 and 1, 2 and 4. And the complement would be like 1, 3, 5, 6, 7, and so on. But it can go to infinity. So to go from here to here, what I do is imagine I put a boundary between the first one and the second one because I have a 1 here. And I look along my complement. I go from position 1 to pipe, I think pipe 1 to pipe 2 to pipe 3. Sorry. I have to go from pipe 1 to what am I doing here? Pipe 3, and then I need to do 4 and so on. And I take the first time that I cross this boundary, and then I swap these two. So here I would, what am I doing here? This is so hard to decode. Oh, sorry. I don't start there. I start from the other one. Sorry. So I start from this one. I have 1, 5, 3, 2, 4. And I draw this boundary. And I look at the first time I cross. And that thing will be when I go from 1 to 3, I cross right away. So my JL here would be 1, and JL plus 1 would be 2. So I swap 1 and 2 to get to this permutation. And this case is very similar, but I only need to take something else. Like my I is still the same, and I almost take the same set, but I only take it starting from somewhere, and I also have a special thing I put in. But I also do the same thing. I go uh, along this set. I find the first place that I cross the boundary that I set here, then I swap at that first place.
Mm, question about the fourth step. You said your JL is 1 and JL plus 1 is 2, but 2 is not in the complement, right?
I think that plus 1 is supposed to be not supposed to be in the subscript. So there are 2 plus 1 here, I think. This one is in the subscript, but this one is probably not in the subscript. Awesome. Wait.
Okay.
Yeah, now I'm confused too.
That's fine. Yes.
Okay. But okay, you can probably look at my paper because I'm also confused now. It's been 3 years, but that is like the idea. You just look where they are. The first time you cross the boundary, you swap them.
I also had a question. So
Yes.
in this fourth step, is it clear that like a simple transposition appears at most once, or could you have like
Yes,
a
because
braid?
yeah, it would be clear because when you do JDT, you swap two things, and then like the next JDT would not go that far.
Gotcha. Okay, so you don't need like a multi-set or anything.
Also, I just realized my mistake. This thing is not S2, S4. This is X3, S4. So my I is 3, 4. So my set is like 1, 2, 5. And when I go from 1 to 2, I did cross the boundary. Thank you for pointing that out.
Nice.
Okay. Any other question? Okay. Yeah, so that is my growth diagram. And so that's my egg. And yeah, I would love to see like what like it's still open. Like the open question is what geometry is this growth diagram holding? And I don't know that is an open problem that I would love to know more about. So if you have some idea about what geometry yeah, I'm getting on here, please let me know. But yeah, if there is no other question, let's go to the second case. And to talk about the second case, I would need to change how I think about the normal RSK. So remember, normal RSK, I have two flags and I have some operators that is nilpotent on both two flags. Then I take the Jordan type of some restriction and I get my P and Q and everything in the growth diagram. Now I want to think about it in another way. I want to say I have two separate vector spaces with these bases E1 to En and F1 to Fn. And I take a linear transformation from V to W that send a basis EI to the basis FW of I. And I want to take a generic T2 go in the other way so that when I do T1, T2, it is nilpotent on my first vector space. And if I want to do the other way around, it is nilpotent on my second vector space. And then I can interpret RSK as just reading the Jordan form of either T1, T2 restricted on W or T2, T1 restricted on V. So let me do an example. This is my permutation. And so this is telling me that my T1 will send E1 to F3, E2 to F1, E3 to F2, E4 to F4. And I want to take the generic T2 go in the other direction so that they are nilpotent on both, and the product is nilpotent. So the generic one would be sending F1 to 0, F2 to E2, F3 to 0, and F4 to E4. And if you take the composition T2, T1, it would send E4 to F4, and then F4 will be sent to E3, so it would send E4 to E3, and E3 to E2 and 0, and it will also send E1 to 0. The other way around, I would send F4 to E3, but then E3 to F2, so I send F4 to F2, and F2 to F1 and 0, and F3 to 0. So if I take the Jordan form of this restricted to like E1 to EI, I get this sequence, these two sequences of partition. So here, if I only restrict it to E1, I send E1 to 0, so I have one block. If I restrict it to E1 and E2, I send both of them to 0. So I have two Jordan blocks of size 1, so I have the partition 1, 1. I restrict it to E1, E2, E3, then I have 2 and 1. And if I, on the whole subspace, the vector space, I have 3 and 1. And similar here, if I restrict it to F1, I have one block of size 1. If I restrict it to F1, F2, I have a block of size 2 because F2 go to F1 and 0. And then if I restrict it to F1, F2, F3, I have 2, 1, and so on. And these are my two tableaus. So this one will give me Q, and this one will give me P. Okay, anyone has any question about my point of view?
Just a question about how so T1 is defined using the W. How is T2 defined again?
T2, yeah, T1 go from V to W, and T2 you just try to take the most generic one, go like linear transformation going the other way. The only condition is that these two products has to be nilpotent. Yeah, and the reason why I think about it this way is now I can generalize it. I can, first of all, I can allow them to have different dimension. So one has basis E1 to EM, the other F1 to Fn, and they can be different. And so because they are different, my T1 doesn't need to be full rank anymore. It can send some basis EI to something in W, but it can send some other thing to 0. And then I do the same thing here. Take the most generic T2, and then I can restrict on this basis to get my RSK. And because I do this, my W is no longer a permutation, but in some sense, like for us combinatorialists, we call it partial permutation. For like rep theorists, they call it partial matching. So I will use the word partial matching, but it's sort of the same as partial permutation. And because these two have different dimensions, my two tableau P and Q aren't necessarily the same shape anymore. So let me do an example. Now I want my V to have dimension 5 and W only have dimension 3. And I take T1 to be this. So I send E2 to F2, E4 to F1, everything else to 0. And I try to find the most generic T2 going back. I would get something like this. So I would send F1 to E3, F2 to E1, and so on. This would need some computation to convince why this is generic, but just trust me. But the point is, I can do the same thing. I can take this composition, then I would send E2 to F2 and then F2 to E1. So I send E2 to E1 and so on. And I can do the same thing. I restrict to like subspace bound by E1 to EI. I get the Jordan form and so on. And I get these two tableaux. But you can see that one is a standard Young tableau with 5 boxes and the other only have 3. So they can have different shape. But the point is their shape can't be too different. Like imagine if my Q is like this shape, then it's very unlikely that my P can be this shape, right? Because these T2 with T1 and T1, T2 are related somehow. So they are P and Q have different shape, but their shape can't be that different. And to record that information, I will also have a third partition that I'm keeping track of, meaning I will take T2, T1, but I only restrict on the basis that has non-zero image. So here I would restrict on E2 and E4. Then sort of when you restrict on E2 and E4, you have like a permutation 2, 1. So my shape is 2, it's 1, 1. And the part that's telling me that P and Q are not so different is recorded in the fact that the columns of my new partition lambda has to interlace between the columns of P and the columns of Q. So this one is saying the first column of P is 2, the second column is 1. So the first column of my lambda has to be somewhere between 2 and 1, and also somewhere between 3 and 2. And so between 2 and 1 and 3 and 2, the only way I can do is 3. Okay. So my third partition is telling me like P and Q can't be that far from my partition. So I would want an RSK to give me this information. I want a standard Young tableau tell me what happens in F, another standard Young tableau tell me what happened in this E, and the third one tell me like how they interact with each other. And I want to also point out that in the literature, this thing is called like type 2 theta correspondence by ref theorists, and these are like A-B diagrams. But essentially, like they just record like which way the arrow go from T1 to T2, T2 to like from V to W, W to V. But I translate that into this partition and it gives me the same information. So this is my egg. Anyone has any question about my egg? Okay, so I have an egg and all I need to do is create a growth diagram and find local roots. So I know my growth diagram would look something like this because of what I know in geometry. So I put RMT, sort of RMT here, RMT here. These are non-empty, but they have to be 1, 1, 1, 1, 1 because this is saying I have a lot of vectors in V, but nothing in W, so everything go to 0. The only Jordan form I get is like 1, 1, 1, 1, 1. So my top row and my leftmost column is fixed. And I put the axis in according to my partial permutation. So 2 go to 2 and 4 go to 1. And by geometry, I know exactly like what I should put in every corner. And because of that, this one is the lambda that I put in. If you go along this row and you look at the first partition only, you get the Q that I want. And if you go along this column, you look at the second partition only, then you get the P that I want. So this is my growth diagram. Every information is in here. And all I need to do is like create local rule. And I can tell you the first local rule is my partition, my third partition lambda here follows exactly the classical RSK. And this makes sense because like to get this partition, I record the part that don't have like zero image. And if I restrict to that part, I sort of have classical RSK. So it's kind of obvious that my third partition has to follow classical RSK rule. And all I need to do is find the remaining ones, and that they are like 10 or 12 of them. And I got lazy when I got to this point, so I didn't write everything out. But they are not complicated. Okay, anyone has any question? Yeah, but the punchline is because I know the local rules now, I can define this growth diagram to be my RSK. So I get my chicken. And because you have the local rule, you also have something like the Venus-Shadow description, because all you need to do is you put together things that have the same shape. So if I look at the first one, I can put over like the places where my first one are the same, and I get something that looks like this. And this is sort of Venus-Shadow description. So we do have a Venus-Shadow description just by staring at the growth diagram. And I will also tell you later why this Venus-Shadow description kind of makes sense in this case. But a question, like if you see my rules, the question that would definitely come up is, why is my chicken not symmetric? Because like if you look at this square, for example, these two are not comparable. So my rule actually say if you want this partition, you have to particularly get from this one. So when you transpose it, you no longer have that symmetry. So the chicken is beautiful, but it's not symmetric. And the answer for that is my chicken are not supposed to be symmetric, essentially. Because why did we expect that to be symmetric? Because we want some involution from W to W inverse. And in representation theory, that is not the bijection that people care about. The bijection people care about is called the Fourier bijection or the conormal bijection. And the story is you have V, you take a cotangent bundle, which is like V times V dual, and you get the moment map because V, you have an action of GLV. So you take the moment map to GLV dual, and you can take the inverse image of 0. The inverse image will have some irreducible components. And a fact in graph theory is that these irreducible components are indexed by GLV orbits in V. But what we can also do is we can also think about the cotangent bundle of V dual, and you do the same thing, then you would also have that these irreducible components are indexed by GLV orbits, but in V dual. So all you have these two bijections, so you have a bijection going from here to here, and people call that like the Fourier bijection or something. And in some sense, that is the correct bijection in that theory. And in combinatorics, this bijection has a very simple description. So this is my partial matching. What I do is I put some extra axes where in the rows and columns that don't have axes, and I draw this shadow line. So I sort of, you imagine you have a source of light here, and like pointed this way, and you see like which point you get, and then you get this shadow line. And what happened after that is you, instead of keeping this corner, you mark the other corner. So I mark this corner, this corner, this corner. Then I would have these axes. And then all you need to do is transpose the diagram, and this is the corresponding partial matching. So, and if you apply our RSK, you do get that when under this bijection, the P and the Q essentially swap. And my lambda bar are not the same, but they are also related. They are related by essentially to get lambda bar, you toggle lambda. And what does toggle mean? We said that the columns of both of these partitions have to interlace the columns of P and Q. So both of them are bounded by the mean of the ith column of P and Q and the max of the I plus one column. So by toggling, I just mean that you take the sum of mean and max and you subtract one, you get the other. It's sort of like you have mean here, max here, and the columns of lambda bar and lambda are like jumping around in between. And so this is indeed a correct bijection, and because of how the bijection works, the Venn of shadow description that we're gonna write is actually makes sense. And yeah, that is the end of my talk. Thank you for listening, and if you have questions, feel free to ask.
Yeah. Any questions for CERN? If not, we can stop the recording.